I would like to invite Professor Robert Babuška, who will present the results of the project Robotics for Industry 4.0. Robert.
Thank you. Thank you very much for the introduction. Yeah, good afternoon, everybody. I hope you can sustain one more talk before the lunch. So thanks, Josef, for already introducing robotics in the context of machine perception, and I'm happy to continue in this trend. So I'll be reporting on the project that's called Robotics for Industry 4.0. And I actually still have a double affiliation. So next to my CIIRC appointment, I'm still a part-time professor at the Delft University of Technology, where I lead quite a large team focused on robot learning and control systems. So I wrote down robots are all around us. Maybe it's a little exaggerated. If you walk around the street, you don't really see that many robots. But if you look more carefully, you do see robots. If you go to industries, let's say a car factory, you will see robots welding systems. And actually, they don't look much different than in the 1960s when they were introduced. So these are pretty lump, dangerous machines without much perception, actually without any perception, just doing repetitive work. Luckily, more robots are being introduced. This is a picture of Baxter and Sawyer in the brotherly embracement, an attempt to introduce collaborative robots. So robots that are much lighter, much safer to interact with, and that you can put standing next to a human worker at the production line, for instance, and the human worker can actually teach the robot by grabbing its arm and showing a specific task. Unfortunately, the company who introduced these robots is already bankrupt, so you can see one of the problems in robotics is that it's extremely difficult to bring new robots to the world. It's a really painful and very expensive process, and there's a lot of gaps and challenges I'll be talking about. More recently, you see these kind of robots. This is the Stretch robot from Boston Dynamics, which is a mobile base, very quick, very agile, with a robot arm. And it has a suction cap or some other type of device, and it can very quickly grab boxes and transport them, for instance, from a truck to a box or something like that. Then, of course, besides manufacturing, you have many other robots. An example would be inspection robots, which you can insert into pipes, let them drive through the pipe, and with the help of sensors, inspect the quality of the walls and these kind of things. If you go to the medical sector, you have the very famous Da Vinci system, but also other more recent robots are upcoming, which are very helpful for certain type of operations, actually improving the performance of the surgeon by quite a margin in specific sorts of operations, like prostate, for instance. And you can go on and on. If you count, for instance, drones or quadcopters as robots, you start seeing more and more of these in inspection tasks, for instance, in industrial applications, but also in mapping, restoration work, and you name it. Of course, all kinds of semi and fully automated vehicles, except for personal cars, which we don't yet have in the streets, but there are dedicated zones, for instance, where you already have fully automated transportation available at airports, for instance. And if you go to consumer products, you can these days buy lawnmowers, and you can buy vacuum cleaners and all these robots. They are actually the most robots sold in the world are vacuum cleaning robots. That's quite obvious, I think. And there are quite futuristic robots coming. This is the Optimus by Tesla, which is not yet ready for the deployment, but it's being showcased already. And it's meant to be a kind of industrial helper and also service type of robot that could do all kinds of versatile tasks in environments where you need actually bipedal walking. So it doesn't have a mobile base as we are used to, but it's a bipedal robot with all the complexities involved in there. Okay, so you could say there's lots of robots, so what's the problem? Why should we do research? And there's also a huge potential for robotics, right? So robots are supposed to take away the dull, dangerous, and dirty work, and by that we get very easy, safer, and much more pleasant work left over for us to do, which is definitely a big step forward. They also have the potential to deal with demographic changes. As you know, the birth rates are declining, the populations are aging essentially throughout the whole world. So there's an upcoming issue with the lack of workforce, basically. And robotics is at least a partial problem to these issues. We still have to reproduce as humans, clearly, but that's a different thing. Energy and material efficiency can go up. If you robotize, you can make processes much more efficient, not necessarily due to the robot, but because you have to think about the system as a whole, and you have to make it more efficient. And also, you're logging lots of data, and you can use this data to monitor quality, to do improvements in your process, and so on. You can also bring production back to countries like the European car countries, and therefore closer to markets, with all the advantages thereof, and reducing, let's say, transportation costs and all these kind of things. You can improve the healthcare, you can improve the quality of life, so you could say there's a lot to gain, but yet robotics is not so widespread as you might think. If you look at this, we are 100 years down the line from this famous movie, and we still have processes like this. On the right-hand side, you see an example of a horticulture production line in the Netherlands, which is not very far from the Delft University. And my colleague used to work on robotizing this problem. And this proves to be extremely difficult. You could say, what's the problem in inserting this yucca stem into the pot? It looks very easy. It's not. It's not. It's extremely difficult in terms of sensing, the manipulation skill, the force sensing that you need to involve in this task, and so on and so on. And this is one example from horticulture, but you can go to any industrial process. There's a lot of manufacturing that's still done by hand. In the break, I've been discussing with colleagues, Airbus is producing aircraft. The fuselage is essentially assembled by hand. All the nails, all the screws, everything is done manually. And it's extremely difficult to robotize these kind of things. So why is that? There's lots of challenges that you have to face. We have seen a wonderful talk on perception, but in robotics, perception is not enough. You have to integrate it with motion control. The robot has to do something, has to correct the motions as it perceives the change in the situation, and you have to integrate it with other things, like dexterous manipulation, for instance. If you grasp an object that is not fully known, that's not described by a CAD model, you have to feel what you're grasping, and you have to accommodate the forces that you apply, and so on. Learning, of course, if you program a robot to do a task, and if the environment is complicated, you're going to achieve, let's say, 70–80% success rate, and the rest will be left over to humans to clean up after the robot. And this is not sustainable for the industry. This is not feasible at all. So what you would like to have is to have this initial, let's say, 80% performance, and then have the robot go on and improve and learn as it gathers data to get, let's say, close to 100%. Human-robot interaction, we obviously do not want to replace humans by robots. We want to introduce them next to humans to help them, to assist them in difficult tasks and so on. So interaction is extremely important. Performance and reliability, if you think about these AI apps you have on your computer, like ChatGPT or anything on your mobile, you're pretty happy with the performance, like 80–90%. And you're quite satisfied. You say, look, it works in most cases. If you put something like that on a robot, it doesn't work at all. It just breaks down each time the robot tries to do something, so it doesn't work. We often think about our cars as highly reliable systems, but if you think about a car, you use it about 2 to 4 hours per day on average. A robot is designed to work basically 24 hours a day. So just imagine the margins for errors that you have if you're applying tools from AI, from machine learning, other fields, to robots to be deployed in the field. And on top of that, it's an extremely multidisciplinary approach. You have to combine expertise in mechanical engineering, electronics, computer science, but not only computer science, but many subdisciplines, machine learning, computer vision, speech processing maybe, control engineering, and so on and so on. So you need many expertise to come together jointly, smoothly. So lots of challenges to face. And our project, R4I, was aimed at addressing at least some of them, right? You cannot address them all, but we tried. So we looked into 3 topics or work packages, if you will. The first one is on robot learning, autonomy, and mobility, with the aim to introduce robots that are much more autonomous, but still do what we want them to do. And by using machine learning, by using concepts like lifelong learning and mobility in unstructured environments. And I will show some examples. Perception, grasping, and manipulation. I think it speaks for itself. And finally, interconnected systems. So systems in which you have multiple robots that should be coordinated to perform a task jointly, and where you also have human workers or human players that can interact with these robots. So we worked in a large team at CIIRC. Here you see a list of about, I think, 18 people. I hope I haven't forgotten anybody here. The first 3 names are people who led the 3 work packages. And then we have a collection of people from very senior researchers at CIIRC through junior researchers, postdocs, PhD students, all the way down to is not the right word, all the way to bachelor students, actually, who joined our team and delivered wonderful work and also made it through to proceed to do their PhD in the end. So all in all, a very versatile and very nice team to work with. We have also collaborators in the Brno University of Technology, the CETEC, which is the Central European Institute for Technology, and we have collaborators in Pilsen, the University of West Bohemia in Pilsen, who are mainly focused on speech processing, language models, and these kind of things. And the Brno people mainly work in drones and mapping perception of the environment and fields like this. So about the achievements, I think the main achievement is that we have created a large team at CIIRC and also collaboration across several departments. I think if I count correctly, we work at least across 4 different departments, including the group of Eugene and of course also of Pepa Urban, with whom we are also continuing the collaboration and starting some new projects. So we are part of the European networks that have been mentioned, Alice and Claire. And we have also managed, thanks to great efforts of my colleague Libor Přeučil, to get IROS 2021 to Prague. And if you know something about robotics, there are 2 main conferences, ICRA and IROS. So we were extremely proud of this step and hosted this conference. Unfortunately, in the COVID lockdown, so that was not that great, but the conference itself was a big success. Yeah, I've mentioned this already, and we have also embarked upon follow-up proposals. So there is a follow-up proposal called RoboProx, which is the Jan Amos Komenský framework, and a huge effort headed by my colleague Zdeněk Hanzálek. And we have a project to start very soon, which is called CoreSense. It's a hop-on European facility, and we are joining a team of many universities from Europe to continue our work, also jointly with Josef and his people. We have contributed to building lab facilities. Yesterday, some of you might have seen the testbed. So part of the testbed equipment was also purchased and made operational within this project. And colleagues of ours working under the leadership of Carla, she's not here today, they have established what is called the Imitation Learning Center for Robotics, and you will see some pictures of that soon. And we have published about 100 or a little more papers in international journals and conferences. So if you are interested, I'll give a link in the end. You can go and check what's up there. So I want to show some selected results now, just very briefly to give you some flavor of what we have been doing. The first one will be on vision-based navigation. The second one will be on algorithms for data-driven, but still physics-oriented modeling. That's something that you definitely need in robotics. And the third example will be on human-robot interaction and also collaboration among multiple robots. So first, vision-based navigation. One of the major problems if you want to deploy robotics in applications like, let's say warehouse management or logistics, is that these are typically indoor applications, and without putting any additional infrastructure, you cannot actually navigate these robots because there is no GPS available indoors, or not reliably, and therefore you have to put some additional instrumentation to actually make the robots applicable in that environment. So that's a difficulty. So what we aim to do here is to use the onboard camera of the robot as the single sensor that is used to navigate the robot, as what we do as humans, right? Basically, you look where you want to be, you compare, you look where you are, you compare that with the image that you foresee as your goal, and then you somehow navigate toward that destination. And we also involved here reinforcement learning as a method to learn not just any plan, but preferably an optimal plan. So minimizing, say, the time or energy that you need to get to your destination. So how do we do this? So we have an observation from the camera, which is an image, the upper one, and then we have a target, which is given by another image. And then you use these two images and you feed them into a deep neural network of the standard, let's say, convolutional type. And at the output, the network spits out signals that are used to directly control the robot. So in this case, we used the wheeled platform, the TurtleBot. So we basically gave commands to the two wheels that just tell the robot whether to go straight or turn at a certain rate and so on. So this is called the end-to-end learning. So from perceptions, basically directly to control commands to the robot. How do you train such a system? Because it's a neural network, it's a black box, so it has lots of parameters. So we used simulation environments like the DeepMind Lab, the House 3D, or AI Tour, which are essentially photorealistic, up to a degree, 3D models of environments, and you can simulate the robot moving in these environments, and you can train the system. So if you do that, it takes a couple of tens of millions of frames, so it's a long process. It takes about almost a day to train this system, but in the end, you can basically navigate. So if you do a simulation then, you drive the robot around. On the right-hand side, you have the target image. What you see on the left-hand side is the current view of the robot camera, and in the end, it navigates to the location where it's supposed to be based on the target image. Maybe not perfectly in this case, but it makes an attempt to get there, right? So you can evaluate how accurate it is, and so on and so on. Now, we also deploy this on a real robot. There, you obviously cannot use the simulation environment because that is very different from your lab or from your warehouse. So what we did here is to use this robot to collect images of the environment, and then we used our own kind of simulator of that environment to train the already pre-trained system that we had to recognize the images from this environment and navigate in there. So it all worked nicely, and it's published in a paper that you could have seen at the bottom. The next application I'd like to highlight is efficient learning from data. And here I don't mean learning in the previous sense, where you pre-train the robot in simulations. Here I mean mainly learning from the experience as the robot is deployed in the world. Robotics is very strange in the sense that you're engineering a system where you know part of the system very well. That's the mechanics of the robot. You know the joints, the inertias, the motor parameters, all these things. And you don't know a large part of the whole system, which is the environment of the robot. The user can deploy the robot virtually anywhere. It can be used to manipulate light objects, heavy objects, soft objects, hard objects. You just don't know. So ideally, what you would like to have is a system that can learn from data as it operates to optimize its performance. And now this learning is very difficult. If you compare it to learning, let's say, large language models, which you feed with all information that is available, this is a very different ballpark, because you have no data. And as the robot starts operating, you are gathering a few data points, and you would already like to have a model that helps you to operate the robot well. So you should learn very quickly from small amounts of data points. And these data are not perfect, right? They will be noisy, there will be outliers, sometimes some signals may disappear or fall out. So you have to face this kind of uncertainty that's inherently present in data gathered online, real-time, from sensors. As you go on operating the robot, the amount of data increases, but unfortunately, the information that's in the data will not increase necessarily. You'll be getting about the same data all the time, because many tasks are repetitive. So the robot is doing the same thing, and it's gathering essentially the same data over and over. So you have to somehow filter the data so that you can filter out those data points that are interesting, that add something new, and basically ignore the rest so that it doesn't overwhelm your learning system. And what you like to have, of course, is that you improve the performance over time. So basically, the robot doesn't get worse. If you work in neural networks, you know the term catastrophic forgetting, which basically means that the neural network beautifully learns up to a point, and then all of a sudden it starts to forget. It starts to do things that it was not doing before, maybe hallucinates, you could say, in current terminology of the LLMs, and so on. You absolutely don't want to have this in robotics, right? You want to have a nice continual improvement of the performance. So an example of methods we use are methods that are capable of learning analytic models, so basically equations from data. So no deep networks, but analytic equation models. These methods are called symbolic regression. It's a bit unfortunate name, but anyway, I'll explain how they work. So you have some set of experimental data that may represent some unknown function. Here you can think of anything. Maybe a robot manipulates an object which is unknown in terms of its mass. And you want to model how the arm with the object in hand will respond to the motor commands. Or it grasps an object with unknown structure or unknown stiffness. You want to model how the object will respond to your grasping force. And you can go on and on and on. There are many examples of how you can apply this technique. Then we use typically genetic programming, but you can use other techniques, neural networks, transformers, and so on, to actually create an equation. Through this evolutionary process, you can synthesize from some primitive functions a larger function, which is shown here, and that gives you an analytic model which hopefully nicely, smoothly fits the data. But this is not working satisfactorily, because the data, as I said, is sparse, so it doesn't cover the entire region, and typically at the edges you get performance which is not what you would like to have. So what we added to these techniques is the use of prior knowledge. Very often you know things about what you're modeling. You know the asymptotic behavior of your function, or you know that the function is 0 when the inputs are 0, and so on. It may have some extrema that you know the positions of. So you can insert this prior knowledge into your modeling, and that vastly improves the performance. So here's a paper which you can consult if you'd like to know more about these things. And we have also used other methods than evolutionary programming, because evolutionary techniques do not scale well with the amount of data. If you add more and more data, you have to evaluate the fitness function over large data sets, and that's computationally very heavy. So we are looking at neural networks, very specialized ones that use specific functional nodes like mathematical operators, functions, and so on, and then some learnable weights and some fixed weights, and you can use gradient-based techniques with regularization to essentially prune away some of the weights, and in the end get a model which is very sparse in terms of the network structure, and which you can write down again as an analytic equation, and we can also insert prior knowledge in these type of models. Finally, you can go on, be very inventive in techniques you use. We can also use transformers, very similar to the language model, to essentially synthesize the function. So we give, in the training set, sets of data and sets of corresponding functions. We tried single-variate and bivariate functions, hundreds of thousands of functions, and you train the transformer basically to look at the data and tell you this is the function I think would fit this data, and also give you parameters. So in this case, for instance, this looks like a sine, and the parameter is 0.2 in front of the argument x. So it's a combination of symbolic generation with some local gradient search for the parameter tuning. And the advantage of this approach is that you spend a lot of time in the training, that's okay, but then when you deploy it, it takes just a few seconds to give you the model for a completely new data set that you haven't seen before. So these methods, I think, have a very large potential. The final example is human-robot interaction. So you probably know that programming robots is very costly. It costs an amount, let's say $1 million, to buy a robot, and it will cost the company about the same amount of money to actually get the robot programmed and verified so that it does the task for which it is acquired. So this is a huge cost, and many companies just cannot or do not want to go into this. So the idea is to use humans as teachers for the robots, in a similar fashion that a human worker with a lot of skills and lots of experience would train a novice in performing a certain task. And what you would like to do here is, I think, similar to what we have seen already, is to integrate different modalities. So, for instance, vision and speech to start with, because this is the way that humans would normally communicate and teach one another. So to that end, we have some centers or some laboratory facilities designed that allow you to use human input. Like on the left-hand side, you see a gesture, for instance, pointing to an object. The gesture gets recognized, and the robot executes a specific task. Or we use multiple robots, and we can do all kinds of training of these robots. An example is given here. So we have the system instrumented with cameras and also with trackers. So you can put a little device on your tool. So for instance, here, it's a grout float, or you can use a roller or a glue gun or tools like that, instrumented with this tool. And then a human worker would execute the task as normally, right? So basically, you're watching with a camera, and you are measuring the ground truth with this tracker. And then you can use techniques like 6D pose estimation methods to actually estimate the exact pose of the tool. And with that information, you can already feed the robot the trajectories that it could execute in order to carry out the task. Maybe not perfectly in the beginning, but hopefully you can use learning then to improve on this execution. And this is very different from the kinesthetic teaching, as it's called, where the human worker has to grab the arm and basically show by pulling the arm what the task is. This is very awkward, and this would be, in certain situations, it would be unacceptable, for instance, if the robot is very heavy, dangerous, and so on. So this is very unintrusive technique to use human inputs for robot training. And we can use the same setups for teaching robots to work collaboratively or optimizing them to work collaboratively. Like in this case, you may have two robots with their own workspaces that would overlap, and the robots could jointly carry out a certain task. So for instance, in this video, you see a simulation, which you can readily deploy on the actual robot, because these are high-fidelity simulation models of, in this case, the KUKA arm. And you can do tasks like, for instance, inserting bolts and nuts. So one of the robots inserts the bolt, and the other robot tightens the nut, for instance. Or they can do welding and deburring and these kind of things. So I hope this gave you an impression of what we have done within the R4I project. In the end, I'd like to acknowledge, of course, CIIRC with Professor Mařík as the director who actually brought me here, back here to Prague. And of course, the funding, which has been very generous and gave us the opportunity to do all these things that we have done, as you have seen. And of course, the whole team, and also the people who supported us through the whole project. So many of them are here in the room, so let me use this opportunity to say a big thanks for your support. And if you would like to see some more information, please visit the website and check what's up there, including the publications and more details about the work packages. Thank you.
Thank you. And now I'll ask for one single question, no more. This presentation will be followed by a visit of the test bed, so you can see some robots in operation. We will start in 4 minutes with the tour. So, who wants to put the last question of this morning? It's already afternoon, but of this morning. If none, nevertheless, there will be discussion in the afternoon, and it's the whole morning is preparation for panel discussions in the afternoon. So there will be additional opportunities to put questions, and I would like to thank you once more for your participation in the research program, for your coming to Prague and staying with us, and for your presentation